Hello, everyone, and welcome back to this session of Bioinformatics Bootcamp. My name is Henry, and this is our second module of this IBMS pre-mat course. And today we're going to be finishing up from last time the lecture, and we're also going to be talking about the homework problems. Okay, so let's go ahead and get started. I'm going to share my screen here. Okay, so this is a reminder to please go ahead and get the code from our workshop repository. So go ahead to our website, bigbioinformatics.org. That's bigbioinformatics, all one word, .org. Come over here to workshops, R for IBMS. You can see here we've got the lecture up from last time if you'd like to go through it. But you're going to go right over here to our GitHub workshop repository. And all you're going to want to do is come over here to where it says code. Go ahead and download that. Okay. So hopefully everyone's following with me here. By the third or fourth time we do this, it'll feel pretty automatic. Go ahead, extract that. Open up the module 2 folder. Then open up that R project right there. Oh, just take a second and the RStudio should pop up. Yep, there it is. Oh, okay. Being a little bit slow today, but there we go. Okay, finally, go ahead and open up the R for biologist.R script, and we're back where we left off. Okay, so before we actually jump into today's lecture, does anybody have any questions on anything we talked about last time? Any questions about numerics, characters, logicals, about simple mathematical and logical operations or variables? Any questions on any of these topics? Okay, well, if questions arise, feel free to put them in the chat and I'll make sure that we stop and get to them. All right, any questions on vectors or data frames? Okay. All right, any questions on lists, matrices, factors? Okay, if not, then we're going to go ahead and just jump into the intermediate concepts today. Again, if you have questions, okay, so Francine asks, can we go over factors again? Sure, I'm happy to go over those again. So factors, if you recall, they are very similar to vectors. So if you look back at the vectors, you can see here they're very straightforward. They're just a collection of simple objects in R. So just a collection of logicals, numerics, characters. And they have a particular order. Factors are very similar to vectors, except that they have additional information associated with them. So when you make a factor, you can see that not only does it contain this vector, but it also contains levels. Okay, so levels indicate the order of the, sorry, I'm trying to define levels without using the word levels here. Levels basically tell you about things that are in that factor, and they tell you the order of those things. So let's give a separate example here that might be more helpful. So let's say that we have a factor that contains some athletes. Okay, so let's say that we have Sarah. No, let's do grades again. This is just a fairly simple example. So let's say that in the class we have grades. So we've got we've got someone who's got an A, we've got someone who's got a C, D, A, B, B, A. All right, so let's say that this is what we have. Now, if you look at the factor levels, you can see that even though the vector contains duplicates. So it's got 3 A's, it's got 2 B's. The levels are just the singles and they have a particular order. And the reason for this is because a factor refers to the idea that even though you have a collection, the duplicates within that collection could pertain to a particular category or type. So in this case, A is a type of grade you can get. We may have multiple instances of A, but A itself has a meaning. It is a level within that factor. Hopefully that kind of makes sense how R is distinguishing between these and why it might be useful to have this. So for example, if it was in fact the case that A was the lowest grade and D was the highest grade, then we would want to reorder our factor. Okay, so let's say that this is grades. So levels of grades is A, B, C, and D. Well, let's say that instead the level should be in a different order. Let's say it should be D, C, B, and A. We can do that. And now when you look at grades, it's in the opposite direction, right? Oh, sorry, I made a little bit of an error here. Well, all right, you get the general concept. I'm not the best at using these because I literally never use them. But just know that this is sort of how they work. That's embarrassing. All right. If you directly assign the levels, you can actually end up changing the underlying data as well. So this is actually not the correct way to do this, apparently. Don't worry too much about it. You really won't use these very often. They're genuinely kind of a nuisance, in my opinion. All right. So don't do what I did here. That apparently doesn't work. Anyways, let's move on now. So any other questions that arise, feel free to put those in the chat. Especially if they pertain to things that aren't factors, I'll probably be able to answer them fairly well. Okay. All right, so let's go ahead and talk about some more complex data structure methods. We're going to talk about methods with numeric vectors first. So let's say you make a vector, contains the values 1, 10, and 4. If you were to add 1 to this vector, what would happen? Well, it would pairwise or element-wise add 1 to the vector. So we get 2, 11, and 5. It just went through and added 1 to each. But let's say instead you have vector 2. Okay, vector 2 contains 10, 2, and 3. What happens if you add vector 1 to vector 2? Okay, well, instead of adding the whole vector to every element of vector 1, it's just going to pairwise add them. So you can see here you get 1 plus 10, 10 plus 2, 4 plus 3, making 11, 12, and 7. Now, this is our kind of thinking for you, but just know that this is the convention it's going to be using. If you tried to add things in a way that indicates you want to do element-wise addition, it will try to do element-wise addition. If you try to add them in a manner that seems to indicate pairwise addition, it will try to do pairwise addition. Again, it will try to think for you, and you have to watch out for that, but it's also very convenient when in a pinch you need to do some vector operations. Pairwise multiplication works the same. So, quick challenge question. What happens if vector 1 and vector 2 are not the same length when you add them? And why? So what happens? First question is what happens? And then second question is why? And I'll give you all a second to work through that. Okay, all right. Okay, let's take a look here and see what happens. So let's say that vector 2 had a 1 here at the end. All right. Now, what happened? It's not an error. A bunch of people said error here, but it is not an error. Okay, warnings and errors are not the same thing. A warning is just a warning. It's going to let you do whatever you're trying to do, but it's not going to actually stop you. An error will stop you. So what did it actually do here? So where did this last value come from? Okay, where did this last, see if someone can figure out how this last value in the result got generated. 11, 12, 7, we already knew about that. That's just the pairwise addition. Where did this last value come from? See if you can figure that out. I'll give you all about another minute. Okay, very good. Yes, very good. Exactly. It comes from the addition. So this is again, trying to think for you. It says, okay, I can add these, I can add these, I can add these. Oh, wait, what's going on here? Well, this feels wrong, but maybe what they wanted was for me to take the last element of this and add it to the first element of this. So it kind of wraps around. Exactly. So this is what Ritika said. It's again trying to think for you. So that can be a blessing and a curse. You just got to know when it's going to try to do it, and just sort of prepare for that. Usually, if it's trying to think for you, it will give you this warning. So this is nice. The warning, it won't stop you, but it will at least tell you, hey, maybe this isn't really what you wanted me to do. So when it gives you a warning, that's usually a good sign that you should stop and just make sure that you understand exactly what R is trying to do. All right. So just like you can do mathematical operations, you can do comparative and logical operations as well. So we also get this element-wise greater than. So is vector 1 greater than 1? Well, this one isn't, but these two are. So we get false, true, true. So we get back a Boolean or logical vector that indicates the comparison. We get the same thing with pairwise comparisons between elements of two vectors that have the same length. All right, pairwise less than and greater than. These are actually backwards. Pairwise equivalence, non-equivalence. And now we can talk about some logical operations. Right, so you get logical operations on Boolean vectors. So we've got true, false, true. Not vector 3 just negates every element pairwise, or sorry, not pairwise, element-wise. False, true, true. So now when we do this and, it's going to match up each of these and it's going to test whether or not they are both true. False, false, true. That's because one of these was false. One of these was false, but both of these were true. So we get false, true, or false, false, true. All right. Any questions on how these are working so far? It's sort of an extension of what we were doing before. I mean, it is literally an extension of what we were doing before, because we've actually been working with vectors this whole time, whether or not you realized it. But it can get confusing once you start to have vectors that are more than length 1. So any questions on this so far? Okay. Well, any questions that arise, feel free to put it in the chat. I'm just going to go ahead and keep on going here. So we've seen and, we've also seen or now. It works the same way. At least one of these was true. At least one of these was true. And at least one of these was true. So all three are going to end up true. Okay. And we can do the same things with the character vectors as well. So equivalence, hello. We see true, false, false. That's because only the first element of this vector is equal to hello. All right, same things here with pairwise. So aloha, world, exclamation point. False, true, true, because only world and exclamation point are the same, right? All right, so hopefully this is making some sense. I'm going to go ahead and move on to a new operator we haven't dealt with yet, called the in operator. If anyone here is familiar with SQL or SQL, depending on who you ask, you might be familiar with the in operator in other systems. Now, the in operator is really just a test of whether something is found in something else. So we're basically asserting here, where it's a logical test, we're asserting here 11 in 1 through 10. Now, we all know that 11 is not part of the integers between 1 and 10. 11 is outside of that range. So this should give us false. And we see, in fact, it is false. Same thing, 5 in 1 through 10. 5 is within 1 through 10, so we know this is true. True in true, false, false. That is true. Hello in hello world exclamation point. That is true. Not aloha in hello world exclamation point. Can anyone tell me what this will give? It's just a quick challenge question here. What will this one give? Okay, good, true, exactly. The reason is because aloha in hello world exclamation point would be false. And then when you negate the false, it becomes true. Okay. Any questions on the in operator? Okay. Let's move on then to the which function. Now, which is simply a function that takes a Boolean vector or a logical vector, and it just returns the indices of all the true elements of that vector. So let's say that we want to take a vector 1 through 10, okay? And we want to test where it is equal to 5. We see a bunch of falses, false, 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 true, false, 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 because only the 5th element is going to be equal to 5 in this vector. So we ask here with which, what is the index of the true elements in this comparison? And it is 5. Okay. So hopefully that kind of makes sense. There's many cases where it can be advantageous to find the indices of all the true elements in a logical vector. It's just important to know that the which operator exists. We also have the length operator. The length operator, or sorry, the length function is going to tell you how long a vector is. So this vector contains 5 elements, 1 through 5. So the length should be 5. Okay. Now, so far, we've really been dealing with things that are quite basic, and they have to do with many of the aspects of R in which it can be used for simple numerical, logical, and character manipulations. But now we're going to start dealing with some stats. Ultimately, that's where we're going to want to get to in our data science. So it's important to know about the sample function. The sample function is a randomized function. Basically, what it's going to do is it's going to take a vector, in this case, a vector of 1 through 100, and it's going to find 10 random elements within that vector. It's going to just choose randomly 10 elements from that vector. And you'll notice here, every time we run it, we get a different result. And that is because it is random. Okay? Every time it will be random. This can be extremely useful when you're starting to get into realms of statistics in which randomization is a necessary component. We won't really get into that in this course, but just know for the future that this is a very important operation. So Simon brings up a great point, which is in R, you can do something called setting a seed. So randomness doesn't really exist. There's really no such thing as randomness in computer science. There's only pseudo randomness. We can only pretend that things are random. But underlying all random number generators is something called a seed. A seed is what actually determines how a random result gets generated in the first place. So you can actually, in R, you can do something called setting a seed. Now, some functions want you to set the seed within the function. And in some cases, you don't have to do that. In the case of sample, I don't think you have to. I think you can just use the method set.seed. Put in any seed you want, although if you want to seem like a hacker, put in 42. And then when you run sample, it should be the same every time. Oh, just kidding. I guess you have to reset it every time you do it. Yeah. So if you set the seed and then run it, it'll always be the same. So you have to set it before every time you run it. Does anyone know why hackers use the number 42? I'm just kidding. It's not really hackers. It's just computer science nerds. This is like a really geeky question. Okay, maybe people don't know. That's okay. Yes, thank you, Simon. It's the answer to life, the universe, and everything. Thank you. If you want to ensure that this seed is going to be used in the same line, you could just put these two things on the same line, separate them with this, I guess that's called a semicolon. And basically that will force R to run both of these things in order with one keystroke. It can be useful to do that just so that you ensure that the seed always gets put ahead of the sample. They don't get run independently. Anyways, these are all things that, not to overwhelm you, but these are all things that you can consider as you start to get better and better with R. Okay. So we've now talked about sample. Let's talk about some other statistical approaches. Let's say that we have a distribution or a set of numbers, right? 5, 120, 4, 1.5, and 3.333. Let's say we want to know what the maximum value in this list of numbers or this vector of numbers is. So we could use the max function in order to obtain that. We can see max returns 100. That is the maximum value from this vector. We could also do min. Minimum value is 1.5. Mean to 22.355. Median, sum, and standard deviation. In fact, there is a whole laundry list of built-in statistical functions within R. At its core, R is truly a statistical language. Okay. Finally, I want to talk about how you can read to and write from files. In this case, let's take a data frame. We're going to use something called mtcars. If you don't know what mtcars is, just go ahead and type view mtcars, and you'll see it show up. mtcars is a data frame that contains information about various models and makes of cars, as well as statistics about their performance. Okay. It's often what we call, or it's what we call a toy data set. We use it for a lot of practice in machine learning, and as we're starting to get better and better with R, we'll probably come back to it a couple times. Another common one is called iris. Okay, so all right, view mtcars. This was a really good example of a time where if some of you ran into an error, you had a chance to remember the cardinal error you'll typically find as a new R user. So let's create an error here. I'm going to create an error. Could not find function view. Now, what does that mean? So some of you might have encountered this error. What does that mean? Well, it means that literally it couldn't figure out what we meant by this. And when you see this error, it's pretty much the cousin of the error, you know, where we do print and then we do some variable we haven't created before. Object XXS not found, right? So basically, these are cousins of each other, and they basically mean that you don't have something that you thought you had. or you misspelled something. So when you see these, make sure to check whether you've misspelled something. In this case, we used a lowercase v when we needed an uppercase v. You can see it works just fine now. All right, very good. So that's mtcars. mtcars is a data frame. We know that because if we do class of mtcars, we see it as data.frame. Now, data frames can be written to files very easily using the write.csv function. So we do write.csv, we put in our data frame, and we say which file we want to write it to. Go ahead and execute that now. Now what happened? It created this file right here, mtcars.csv. If you go in your file viewer, sorry, I'm looking in the wrong place now. If you go in your file viewer to where you're currently coding, you'll find that CSV file got created. And if you have Excel installed on your computer, you can just go ahead and open it up in Excel. So that's what it looks like. CSV simply stands for comma separated values. It's a type of text file that is ubiquitously used in data science. If you actually open it up as text using a program such as WordPad, oh, right, I have to close it in Excel first. Excel gets picky about these things. If you open it up with WordPad, for example, you can see here that all it is a list of values in quotes or not in quotes if they're numbers and separated by commas. That's what comma separated values means. And basically it's a way of specifying using only text the row names, column names, and values of a data frame. So under the hood, that's what it looks like. The cousin of CSV is TSV. It stands for tab separated values, and it's just another common format that people will use. Okay, so just as easily as you can write a data frame to a CSV file, you can read a data frame from a CSV file. So we use the read.csv command to do that. And you can see it read it from the file into memory, and now I've got it right here. Can anyone tell me one problem with the data as it's been read in? Is there something that made it different from how it used to be here? So if you recall, so let's go ahead and get rid of mtcars from memory here. Actually, yeah, so let's get rid of it from memory. You can select the broom in order to do that. So let's go ahead and view. Yeah, so let's go ahead and view mtcars. I'm probably not explaining something I should explain here. mtcars is always built into R. It's always available. Even if you hit the broom, there's always an object called mtcars that's waiting in memory. Just so you all know, R has these built-in toy data sets for you to play with. So even if there's nothing in our environment, in theory, in reality, mtcars is also there. So instead of calling this mtcars, we could call this mtcars2. And so now we can easily look at them side by side. So all I did to get this was to hit that button up here, and I'll just do it again here so you can see. This is a pop out. Oh, my computer did not like that. All right. So if we look at mtcars and mtcars2 side by side, do we notice anything different about them? Can anyone tell me what's different about them? Just go ahead and visually examine them. See if you can find any inconsistencies. Okay, what do you mean an additional column? What do you mean by that? You're right. I just want to know what you mean. Right. The car brands. Yeah, the car brands are now in an actual column. See, before they were just the row names, right? You could see in the actual MT cars data that's stored within R, they're actually the row names. But when you look at MT cars 2, they've now been called, they've been turned into a column that is called X. Yeah, and so the row names, there are actually no row names in MT cars 2, or well, technically there are row names, but they're just automatically generated numbers. So what's happened here? What's happened here? Does anybody know what's happened here? And I'll give you a hint, and this is going to be an important lesson. If you take a look here at the help page for read.csv, there's actually a hint in there. Let's go through it together. So to look at the help page for a particular function, all you have to do is go to your console and type question mark and then the name of that function. So question mark read.csv. And now we find the help page for read.csv. So here's the help page for read.csv. Now it's actually part of a family of functions called read.table. It just happens to be a particular type of read.table function. Read.table can work with TSVs as well. It can also work with other types of files, but read.csv is a special type of function that only reads CSV files. So read.table, read.csv, they are cousins of each other. And so that's why they're on the same help page, just so you know. Now, we come down here to the arguments that go into this function. And we can see here there's quite a few. So far, we've actually only been using the file argument. How do I know? Well, if you hit tab, if you put your cursor at the beginning here, in fact, I'll just even get rid of this. If you open up the function and you hit tab, you can see the very first argument is file. And so if I say file mtcars.csv, this is actually equivalent to me just putting mtcars.csv in here. Why are these equivalent? Well, the reason is because when you use files or when you use functions in R, you can use them by directly declaring the arguments like this. So I'm saying specifically the file is mtcars.csv, or you can use what's called positional arguments. This hinges on the knowledge that the first thing that is in the function is the file. So whether or not you say the file explicitly, whatever the first argument you give is, if you don't give a name to it, it will be considered as the file. This is sort of a shorthand that is not very good practice, but you'll see a lot of people do it. It's a lot more common in Python as well. It's usually much better practice to actually specify the file or to specify your arguments directly. So that's one thing to note here. The other thing is that there's actually a lot of other arguments we could provide. So just going down here, looking through the help page, can anyone find an argument that might have something to do with how the row names are handled? So can anyone find? Okay, good. Exactly. There's actually an argument called row.names. Now, row.names can be quite a few things. You could actually provide the row names directly. So if you have a vector of names that you want to give, you can actually provide that directly as the row names. But it could also be a vector, or sorry, it could be a single number giving the column of the table which contains the row names. So if we look back at our data in Excel, we can see that the very first column actually is the column containing the row names. Now, in a CSV file, there's no way to actually specify that something should be considered the row names, just like there's no way to specify that something should be considered the column names. There are only conventions. And there's no agreed upon convention for row names in the first place. So what it does is to just not assume anything about your data. R is not going to assume that your first column is row names unless you specifically tell it that. So row names, to actually say which column is the row names and to specify that the first column is in fact the row names, all you have to do is add an extra argument here, row dot names, and you can see it's already automatically filling in what we want here. Hit enter to select row names is 1. And when we look at mtcars2 now, we can see we've dropped the number of variables when we execute this. And if you look at this here, you can see now the row names are correct. So I make a big point of this because one of the things that's very frustrating at first when you're dealing with R is understanding how to deal with this exact issue of reading to and writing from files. And I just want to show you that it's actually fairly straightforward once you understand how to find the help page and how to interpret the arguments. Typically, there'll be a built-in way to do whatever it is you're trying to do at first. Only when you start getting to more advanced topics will you find that there's really not many built-in ways to do what you want to do, and you'll have to find packages that help you accomplish your goals. But we haven't gotten there yet. We'll get there next time. Especially as we start talking about the tidyverse, that will become more and more important. Okay, so before we jump into if else, does anybody have any questions? If anyone's curious about the other built-in data sets that are in R, you can actually access them using a function called data. At least I think this is the right way. Ah, there it is. So just type data, empty parentheses, and you'll actually get the very long list of built-in data sets that are automatically added in R. It's quite a few. Pretty much anything you would be interested in messing with, you'll find a toy data set for it here. Okay. Okay, well then, with that being said, let's go ahead and jump into if else. So if else is just a logical gate. And basically what it's going to do is it's going to open if a logical condition evaluates to true. And otherwise it's going to remain closed. It's part of something that we call control flow. And if you imagine it like this, you're flowing down in order throughout your script. And once you reach a particular point, there can be a decision boundary. And if you meet some condition, the gate will open and you can flow through that part of the code. And if a decision and if the condition is not met, then the gate remains closed and you just skip it. In our case here, we're going to use a gate that checks whether the value of I is greater than 5. Now, in this case, I is 4. So the value of I we know is not greater than 5. If we check what this evaluates to, we can see that it is false. So therefore, if we try to run this section of our code, nothing happens. The gate remains closed. But if instead we change the value to 6 and we rerun this, the gate opens and the code inside of it becomes executable. These curly braces basically represent what's being held behind that gate. The gate itself is represented by the if, parentheses, and then logical condition. Hopefully that kind of makes some sense as to how that's working there. Okay. If else is a way of ensuring that if a condition is not met, the gate isn't simply skipped. You actually do something. So if I is greater than 5, in this case, we know it's not. If I is greater than 5, then we will print I is greater than 5. But if this condition is not met, then we actually proceed to this second side, the else statement, and we print I is not greater than 5. So we see that in this case, I was not greater than 5. So we executed the else part of the gate and we printed the statement. So rather than skipping the whole thing, it's basically just channeling you into an alternative path. Again, this is why we think of this like control flow. People call this sort of like data flow, or I think this is sometimes called procedural programming. But basically, the most common term for this is if else. Now, you might want to have a more complex if else. So let's say that you want to test whether a value is greater than 0. But if it's not greater than 0, you don't want to just do whatever else. You want to also test if it is equal to 0. Okay, and then if neither of those conditions are met, then you want to execute the else. Let's say that that's your goal. Well, this is how you would construct that gate. If I is greater than 0, we'll do this. Else, if it is equal to 0, we'll do this. Else, we'll do this. You can never reach this final else unless both of the preceding conditions fail to be true. In this case, we know this one will execute. If we increase it to 1, and if we make it negative, we see that the else will execute. Okay. So fairly straightforward, but it can be fairly complex once you start getting into greater and greater, I guess, layers of the if else. So any questions on if else? Now, given everything that I've told you so far about how to find the help page for a function, I now have a challenge that I want to propose to you. Can anyone tell me how I could redo this part right here? Okay. How I could redo this part right here, but instead use something called if else. Can anyone tell me how I might do that? So if else, if you go to their help page, you can find it like that. Can anyone tell me how I might be able to adapt this? Go ahead and give it a shot. This is a bit of a challenge. Give you all a couple minutes to work on that. I'll give you all 5 minutes to work on that. That one's actually kind of tough. But see if you can figure it out based off of the help page and based off of the goal here. Okay, so has anybody been able to solve this one? Anyone got an idea of how we might redo pretty much all of this, but with if else? Sorry, I mean to highlight this part. Redo this part, but with if else instead of the more formal if else. Okay, okay, good, good. Very good, Lauren. And Ritika also had the right answer, but I think you accidentally sent it to me as a direct message. Very good. All right, so the way you would do it is where it says test, you would say I greater than 5. That is our logical test, right? Now, if that test proves to be true, which is basically what we're doing here, right? Then we give I is greater than 5. Sorry, I'm like breaking my own rules here. Yes, that would be yes. Else no, I is not greater than 5. Now, just to make this look a little bit nicer, we could actually clean that up by hitting enter after the commas. Okay, so we see basically the same thing that we got before here. So I is not greater than 5, I is not greater than 5. Now, did anyone try to put print in here? Did anyone see what happens if you try to put print in here? Let's try it. This was actually why this was kind of a difficult challenge in the first place, because this isn't exactly like the other if-else statement. So you'll notice it's not giving me 1 at a time. It's giving me 2 back at a time. Why is that? Well, the reason is because if else is a function that returns a value. So we've talked about functions now for a bit. We've talked about functions that return values predominantly, and we'll get to it later when we talk about building functions, what it means to return a value or not return a value. But not only does if else execute this code, but it actually provides you back the result as a new variable. So let's assign this to something. Call this result. So now you can see when we execute it, it only printed once. And that's because the other one, the second one, is now being captured by the variable result. Okay. So hopefully that was a good challenge, good exercise in on the fly learning a new function. That will be what you do a large portion of the time you work in R. Learn new things on the fly. Okay. Any questions on if else, elif, or sorry, it's not elif, that's in Python. If else, else if, or if else, all one word. Any questions on these concepts? Okay. Well, let's go ahead and move on to loops then. So loops are another type of control flow in R. Basically, they're a way of going back and repeating something over and over again throughout the length of a particular vector. So let's say we've got a vector called days of the week. Oops. Monday, Tuesday, Wednesday, Thursday, Friday, Saturday, Sunday. Let's say that we want to go through this vector, and for every element, we want to print that element. So for every day of the week, we want to print that day. Well, we can actually do that using this for loop. For day in days of week, print day. That's the same thing as what I just said. We're going to go through every element in this vector, and we're going to print it every day in the days of the week and print it. For day in days of week, print day. So the way this is working is that days of the week is our vector. And the iteration happens when we go through every element of the vector. And so for every element, we're going to take that element and in order, we're going to assign it to the variable day. And then we're going to do whatever we want with that variable. We could print it, we could add to it, we could do something like we could reverse the order of the letters. But in this case, we're just going to print it. So that's all a for loop is. It's basically in sequence going through a vector, assigning that vector to a variable, and then doing something with the variable in between the curly braces. We call this the type 1 pattern of using for loops. And it's fairly common in R. It's also fairly common in Python to do it this way. Something that you might also see is this type 2 pattern. Basically, this is the exact same thing. I mean, the for loops aren't in any way different, but what's different is how it ends up getting used. So rather than going through a vector, we're actually going through a vector that is of the same length, but numeric. So the original vector was days of the week, but we actually create a new vector called 1 through length days of the week that is the same length as the original vector, but instead contains numbers. Now, these numbers correspond to every element of days of the week. And so we can actually use them as kind of a stand-in. So if we wanted to get day, if we wanted to basically replicate what we just did up here, this is how we would do it. When I is 1, we can grab the first element of days of the week, assign it to day, and then print it. So this is just more of a convoluted way to do the same thing we were doing up here. There are lots of reasons why you would want to do this. There's lots of circumstances in which this arises that you would very much want to have an I rather than having to get day. So let's say, for example, that you had a second vector, and let's call this vector emojis. And so let's say that my emojis here are sad, happy, 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 happy with a very happy and very happy. So let's say that these are the emojis corresponding to the days of the week. Okay, now for every element in emojis, it corresponds to one element in days of the week. Sad Mondays, happy, and then very happy on Saturday and Sunday. Okay. Now let's say that we didn't want to just print day of the week. We wanted to also print the emotion from that day. Well, you would need to be able to grab the emotion. Well, I corresponds to the length of days of the week, but it would also equally correspond to the emojis vector. So we could grab that corresponding emotion by using that I iterator. That's what it's called. I stands for iterator. And we could print day and we could print emoj for that day. So you can see why we might want to do this. If you've got two vectors that both contain information that is paired across the vectors, you might want to use an iterator to grab the corresponding information from both. Okay. Next up, we have while loops. While loops are kind of an interesting beast. You really very rarely use these, but you know, you might find yourself doing it at some point. While loops basically will keep executing some code right up until a condition is true. Or sorry, until a condition is false. Don't know why I said that. So while x is greater than 0, do these things. So X is 5, so therefore X is greater than 0. So it will execute this code. Now, this code contains a component that will decrease the value of X. That means X will eventually be 0, in which case this will now be false. So let's watch it in action. So you can see it goes 5, 4, 3, 2, 1. And then in the last iteration, X becomes 0, and therefore this is now false, and so it stops. So can anyone tell me how I might design a while loop that will never stop? Can anyone tell me what is a way to design a while loop that will never stop? Be mindful that it's not exactly the best idea to execute a while loop like that. But can anyone tell me how you might do it? Okay, good idea. All right. Lauren says change the subtraction to addition. So very good. Very easy way to create an infinite loop. Because if X is always going up, it could never be less than or equal to 0. Now, it's not exactly the best idea in the world to do this. But if you do find yourself in an infinite while loop, what you could do is simply hit the escape key, and that will stop it. If you don't have an escape key, which I know some like newer MacBook users might not have, they've got a bug that refers to that right now. But if you don't have it, you could always, instead of hitting the escape key, hit this stop key up here. This will stop the console and it will get you out of the loop. Okay. No need to panic. Simon says, rule number 1 for while loops. Always make sure the variable in your condition gets changed in the body of the loop, and the condition will ultimately be false. Otherwise, you will create an infinite loop. Yeah. There's really very few conditions in which it makes sense to use while loops. There's really no conditions in which it makes sense to use for loops, but definitely there's very few in which you would ever want to really use a while loop. But if you do find yourself in one of them, well, just make sure that it can end. Simon asks, general interest. Will that loop stop when the number hits the maximum number that R can represent? Does anyone know what the maximum number R can represent is? This is sort of a computer science kind of question. Okay, well, there's actually a way to find that information. If you press dot machine, and then, so what is dot machine? Okay, so let's take a look at the class of dot machine here. It's a list, okay? It's a list. Let's look at its structure now. So it contains a lot of stuff, but basically it gives you sort of, for your computer and your version of R, what are some of the limitations of your computer? So one of the things that we can use is the double X max. This is actually the largest number that my computer using R is able to represent. And it is 1.8 times 10 to the 308th power. Even in a infinite while loop that goes quite quickly, it would take us a very, very, very long time to reach this number. I'm not sure we could actually ever reach it in our lifetimes. Really not sure. But at the very least, you'd be sitting there for a long time. Okay. All right. If you combine the use of loops and if else, you can actually perform some fairly complex operations. So let's say we've got our days of the week. We could loop over these days of the week, and then we could execute some if else logic. If the day is Saturday, we say party time. If the day is Monday, we say I hate Mondays. And if none of those things are true, we say no parties today. So let's go ahead and run through that. So we see here, Monday, I hate Mondays. Tuesday, no parties, so on and so forth. Saturday, party time. Sunday, no parties. So hopefully that kind of makes sense how you can achieve even more complex operations by combining the use of for loops and if else. All right. We're going to talk about functions now, functions and their application in the apply family. But does anybody have any questions before we do that about loops or if else? We're pretty close to the end now. We're going to end fairly early, I think. Okay, let's go on to functions then. So we've got a function here. Now, a function is a type of object in R. It's a special type of object because it's an object that can take an input and return an output. Or at the very least, it can take an input and perform some operation. Okay, so functions tend to look a bit like this. Usually, it's a variable that is being assigned from this kind of pattern here where it says function, then it's got some parentheses in which you provide arguments, curly braces in which you put the code your function executes, and then you can actually execute this function like so. So this is just a pattern you're going to want to get used to seeing. Now our function here is called myfunct, and it takes a number, and then it's going to print your number is, and then it's going to print that number. So let's go ahead and see how this works. We put in 100, and then it says your number is 100. We put in 200, your number is 200. Okay, so you can see how this is working. No matter what we put in here, it's able to process it. Okay. Now, the reason why we use functions is because it allows us to take code that we might want to reuse many times and do so. The input doesn't matter. The code will always stay the same. That is sort of the power of functions. Now, this function doesn't return any result. If we assign the output of the function to something, well, actually, sorry, it actually does. Okay, so R is kind of a funny language. It does technically return a result, but not exactly one that we would care about. If you change from print to cat, so print in R4 actually returns something. If you change from print to cat, which is like kind of an older way of doing prints, you can see that it actually doesn't return anything. It just makes the statement your number is 100, and the output, which we've assigned to the variable dd, is null. So what is a null? Does anybody know what a null in R is? Can anyone tell me how to find the class and the structure of null? Okay, that's close, very close. Okay, good. Class of null. Interesting. What kind of object is this? It's an object of type null. Very interesting. What is the structure of a null object? It just says null. So null, it's kind of a curious object in R. It's really a lack of existence. It basically means this thing does not exist. This thing does not have any meaning, right? It's different from an error because it represents a value that does not exist, right? So the value can be an existing concept, but the actual thing itself is missing. So it's kind of a curious idea. It's more philosophical in ways than not, but just know that when you assign the output of a function to a variable and you get this null object, that basically means your function didn't return anything. It might have done something, but it might not have actually returned anything. Okay. Now, functions typically are going to return something. Usually a function is going to take some data, it's going to perform some operation on it, it's going to transform it some way, and then it's going to return the transformed data. That is usually what you want to do with functions. So let's actually do something like that here. So we're going to make a function called random picker. This random picker is going to take in a vector. It's going to randomly choose an element from that vector. That's going to be our result. And then it's going to return that result. So if we use random picker on days of the week, we can see that it is capable of randomly picking one of those days. Okay, now if we assign this to something, we can see it actually does return a result. If you look in that top right panel, you can see it is returning a result. It's not printing anything, that's okay. It's returning a result. Okay. All right, so that's, in a nutshell, that's functions. One final thing to mention here, you can use your named arguments here. And one other final thing to mention is, if you want to, you can provide additional arguments. So let's say that instead of just picking one element, we could actually pick two. So let's call this size to pick. And we could pass this in right here instead of one. And let's say that size to pick is 3. So we could randomly pick 3 each time. So you can see it changing up here. Now, what happens if we don't provide size to pick? Oh. Oops. Hold on a second. Oh, I've apparently made some sort of mistake here. Oh, I see. Okay, I see what happened. If you don't provide size to pick, it will be, and let's just prove this here. If you don't provide size to pick, it will be missing. And another way to say that is it will be oh, sorry. Okay, I'm trying to think of the right way to show this here. Let's actually, okay, sorry. So I'm trying to find a cool way to demonstrate to you that if size to pick is missing, it will be null. Okay, so if you provide null to size in sample, it actually will pick all of them. So this is where, again, R might do something unexpected if size to pick is missing. And this is why when you're writing functions, it can be beneficial not to leave them like this, but to actually provide a default value. So let's say that our default value is 5. So this means that even if we don't supply anything, there'll be a reasonable default value chosen. So you can see here, picking 5 each time. All right. So hopefully this makes sense. Hopefully this illustrates to you why it is so imperative that you don't just let R do what it wants without making sure you understand what it's doing, and why you check the output of a function to make sure that it actually matches what you expect it to be, because R will try to think for you. And when that happens, unexpected things can arise. You'll get an answer, It doesn't mean that you have a reasonable answer. And it may very well mean that the data you analyzed in the way you analyzed it, that has produced results that are now incorrect, and you won't know that until a peer reviewer says, hey, there's something not right here. And that's very embarrassing when that happens. You'd like to avoid it if possible. Okay. So this is a way of doing functions in the more classical sense. So let's say that we have a function that takes a day and then it returns party time, I hate Mondays, or no parties today. This is sort of the adaptation of our if else from before. And let's say that instead of using a for loop, you actually want to just take this function and apply it to every day of days of the week. So, sorry here, I think I meant to put this as my function. So we could use an sapply to do that. So sapply is going to go through every day in days of the week, and it's going to apply this function to it. So this would be the equivalent of having a for loop like this for day in days of week, my function day. This would be very similar to doing that, but instead we're using an sapply because that is much more efficient and it's much better practice than using for loops. And we can see how this works. Basically, it returns a vector of equal length of days of the week with the results of my function for every one of those days in turn. Now, sapply is a funny animal. It can be a little bit unexpected how it returns. lapply is a little bit more consistent because it always returns a list. So let's say that we do that here. So we've got our list here. I hate Mondays, no parties today, so on and so forth. We can actually add our days of the week back to that list and now get our named list with our results from the lapply. I don't use actual apply very often, but I just wanted to show you how it can be used. So let's say you have a matrix 1 through 10, arranged 2 rows, 5 columns. Actual just base apply takes a function and it applies it to the rows of your matrix, the columns of your matrix, or both the rows and the columns. If you just say 1, that's the rows. If you just say 2, that's the columns. If you say 1, 2, 2, 1 through 2, that is both. So our function here was if number is greater than 5, true, else false. So we see 1, 2, 3, or sorry, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, false, and then 6 and onward is true. So you can see it works. Again, I don't really use apply very often. I don't really see too much of a reason to do it for the most part, but hey, you know what? Some people use it more often. So in this case, you could add up the sums of all the columns using an apply with the margin being 2. So we're just basically returning the sums of all the columns. So 1 plus 2 is 3, 3 plus 4 is 7, 5 plus 6 is 11, and so on. If we, instead of using a 2, we use a 1 here, we're summing up the rows now. All these added up is 25, and all these added up is 30. Okay. So I would say that's pretty much it for today. This is a fairly good distillation of introduction to R and intermediate R, but I want to see you actually put this into practice. Now we have a homework, and the homework is quite difficult. You've had a couple days now to work on it, and you're going to get a few more to continue working on it. The first set of problems all the way up until the challenge problems start down here. So everything up until line 74, I would say these are pretty good fill in the blank problems. They'll get you thinking, and they'll get you familiar with a lot of the concepts that we've now talked about. then when the challenge problem starts, you will be asked to apply that knowledge in fairly realistic challenge problem settings. I'll tell you, pretty much everything from super challenge problem onward is fairly representative of things I have to do on a daily basis. So I would argue if you can get to this point, that would be really good. See how far you can get. So I'll just say right now that if anyone can get to the good luck you're going to need it challenge problem, please let me know. I might want you to collaborate on some stuff. But at the very least, see how far you can get. And especially if anyone is able to solve this tic-tac-toe challenge problem, this is a very difficult challenge problem. If anyone's able to solve that, definitely let me know. Okay. Any questions on what we've covered today? Any questions on the challenge problems or on R in general, or on what we're going to be doing next time when we move on to the tidyverse and do a project? Any questions on any of that? Okay, if not, then I'm going to stick around for a few minutes, but if you don't have any questions, then feel free to dip out and have a good weekend, and I'll see you all next time. Yes, these are the same set of problems from Wednesday. You have additional time to complete them. They're very difficult, so take as much time as you need. Hopefully everyone will have these done by next week when we come back. Okay.
I totally missed the answer for that while loop. There was like shit going on off screen I had to deal with. Will it stop when you hit whatever the max number is?
Oh, right. So